I'm going to talk about virtual emulated Cosmos xhaul and why we might want to build it. So, and this is joint work between University of Arizona and Trinity College Dublin. So next slide. If so, optical SDN testbeds like the Cosmos Optical xhaul network are great. Give all kinds of advantages. It's real hardware, real apps, real operating system, real control plane, or perhaps research, but it's running real code on real hardware. You get full line rate execution, real data interactive operation, and most importantly, for something like Cosmos that actually connects to the real world and enables these exciting applications. Also, there can often be accessed remotely and shared. And one thing that's really important to me and probably to the field as well is that they facilitate hopefully reproducible experiments. Dola talked about that earlier about both emulation and reproducibility. I'm going to touch on those things as well. And so, in some sense, hardware test beds really represent ground truth and are kind of the gold standard. Next slide, please. Except, of course, and they're great except when they're not so great. And they're not so great because, well, they're hard and slow to build. I mean, Cosmos probably cost a fortune and took forever to build and is probably still not done. And how are you going to duplicate that? It's very hard. Also, you're limited to the number of devices that you have. Adding new devices requires provisioning them and integrating them in and plugging them in. And you're limited in scale. Like if you want to go beyond the hardware you have, that may be difficult. Also, since it's a shared thing, often there's limited availability or hours, especially during peak times, like during, say, the Cosmos tutorial tomorrow. Other people won't be able to use the testbed because it'll be occupied by the tutorial. Or before a submission deadline. Shared testbeds often tend to be very highly occupied. So shared and limited hours means that you really have limited time for debugging on hardware. And small errors that you make in your scripts can waste your entire time quota. It can be challenging to run tutorials or courses or labs because of demands for availability. Demos will have to be scheduled in advance. And it's hard to run experiments that may take a long time, like days or weeks, because you can't actually occupy the testbed for that long. And also kind of you don't have a lot of time for creative exploration and fun, which is sort of too bad. So next slide, please. So we can mitigate this somewhat with hardware-based solutions, which we talked about some today. Like scalability can partially be addressed potentially by testbed federation, such as Cosmic, where Cosmos is linked to other testbeds. So we could, if we wanted to, like have a larger optical network with more components if we wanted to by connecting these test beds, although there are limitations with that. It also may be possible, probably is, to virtualize, slice, and multiplex the optical network itself, for example, by port and wavelength with some sort of SDN virtualization front end to support shared use. And these are all great ideas that we should pursue with Cosmos, but they don't address all of the issues. And so what I'd like to talk about today is a proposal for a virtual emulated Cosmos optical xhaul network. So I believe that I would like to suggest that Cosmos development and experimentation would be greatly enhanced by this sort of virtual emulated optical xhaul network. If it could run, say, on a laptop or another PC server, it didn't require the actual Cosmos hardware, but would emulate the same devices as the Cosmos optical network, including the SDN and control plane APIs. And so ideally, you'd be able to run the same SDN controller against the virtual emulated infrastructure as the physical infrastructure. So you could test on the virtual infrastructure, make sure everything works, then transfer seamlessly to the hardware for realistic testing with minimal changes. Ideally, it would support a similar user interface and configuration API to Cosmos, and emulators could potentially also connect to the real world. Next slide, please. There's some good examples of precedents of this kind of virtual and emulated test beds already from the packet server world. For example, virtual Emulab. Also runs in a virtual mode that can either run hosted on the Emulab infrastructure in Utah, or it can run locally on your laptop or server. Local cloud infrastructures are another example. You can run OpenStack in a kind of local development environment on a laptop, as well as on an actual cloud. Similarly, something like LocalStack allows you to run something AWS-like on your laptop. You can run local container environments. And in the area of packet networking, we have examples of Mininet, a packet network emulator, which I started some years ago, extensions to it such as Mininet Wi-Fi and also Mininet-Optical, which we're working on now, which I'm going to talk to you about today. And these optical emulator systems can emulate access networks, wireless networks, and optical networks, such as metro networks or wide area networks. And something like Mininet, with its extensions, potentially enables the integration of multiple forms of network emulation in a single framework. So next slide, please. So SDN emulation can really complement and benefit hardware test beds. If we look at examples from the packet network world, this has really played out over the last few years. For one, minimal hardware requirements. You can just download it from the internet. So it's basically zero cost to deploy an emulator or simulator. But the experiments can move semi-seamlessly between emulation and hardware because the same software-defined networking controller and server apps can run on both infrastructures, although obviously not at line rate and full speed on a laptop or server as they would on the actual system. But you can work and test even when the hardware test bed is unavailable, and also hopefully find bugs before the hardware testing deployment, and so you don't end up wasting all your time. So they're currently used in the packet networking world for development, debugging, testing, continuous integration, tutorials, demos, courses, labs, massive online courses, and also modeling real networks. You have a real network and you make a model of it that you can study without perturbing the real network. Or you can run experiments that would kind of ruin the real network, like security experiments. And this has been a huge enabler for research, experimentation, and learning in the packet SDN world with tons of SIGCOMM and SOSR papers and courses. And it's also used to develop major SDN controllers in the packet world, such as ONOS, Floodlight, basically everything, Open Daylight, Ryu, Faucet, etc. And has also helped, as I mentioned, facilitate reproducible experiments, which is becoming increasingly important if we don't want our discipline to just be cold fusion. So next slide, please. So we look at Mininet's design. It sort of gives you a virtual emulated packet network. This is packet Mininet. So you run this virtual network on your laptop, but it runs this, you can run the same SDN controller pointed to that network, and then just point it to the hardware network, and it'll basically work the same way. So wouldn't it be nice if instead of only having these optical network components like these these packet network switches and packet network transmitters, packet network line cards, so basically Ethernet cards and Ethernet links. Wouldn't it be great if we could have optical network components? So next slide, if we could just have ROADMs connected to transceivers and an analog optical network connected to software-defined networking controller. And if that basically could be modeled on the emulator, and the same control protocols and same SDN controller could be used for the virtual infrastructure and the hardware infrastructure. And we've actually been working on doing this, and we've built we're working on building what we call Mininet-Optical, which extends Mininet with a bunch of optical networking simulation and emulation elements. Next slide, please. So most importantly, my colleague Alan has implemented an optical network simulator that simulates the transmission physics of optical networks using the GNPI Gaussian noise model, sort of a steady state, simple but efficient and effective optical network model that we can actually run sort of in semi-real time in an emulation mode. And that is used within the Mininet emulator to create an emulated optical data plane with emulated network components such as ROADMs, transceivers, fiber spans, EDFAs, amplifiers, and OPMs, optical power monitors. And then on top of that, we've implemented an optical SDN API, which is currently REST. And so with this, we're able to connect an actual SDN controller, for example, ONOS, to our Mininet optical network. And we demonstrated this next slide, please, at one of the last conferences before the lockdown, which was OFC 2020 in San Diego in March, where we showed created a network using Mininet-Optical, connected it to ONOS using our REST API, and demonstrated how we could basically have ONOS control both the packet side of the network and the analog optical side of the network, and how we could get information such as the link OSNR, GOSNR, or such as, I guess, on the right I'm showing signals entering POP5 on our network, and we see the OSNR for a variety of wavelengths. And we had a demonstration where we dynamically reroute signals in response to failure of an amplifier. So next slide, please. So what we're proposing is this idea of a virtual emulated Cosmos xhaul, which is to say the optical networking part of Cosmos emulated with Mininet-Optical as a way of doing it. And so we think we can build on the Mininet-Optical design, adding components to emulate Cosmos or the Cosmos xhaul optical network, such as compatible optical SDN control APIs. Currently we use REST, but we need things like netconf and OpenROTM. We'd probably want some kind of simplified emulation of Internet of Things and mobile wireless clients and associated cloud backends. Ideally, we'd have a compatible configuration API so that experiments could be moved more easily between the two infrastructures and runtime API. And possibly even adapt the GUI for virtual and emulated Cosmos. For example, if you look at Emulab, you basically use the same GUI with the emulated infrastructure as you do the physical infrastructure. So it really kind of eases the learning curve. Next slide, please. There's some additional things we could do, obviously, which would be pretty cool as well. We could have more realistic modeling and execution of IoT, where we actually run the real software, although, and perhaps emulate some of their special features. We could have a hosted version of on the Cosmos cloud infrastructure, like virtual Emulab, or on commercial clouds. And also there's this interesting possibility of integration with Cosmos to enable hybrid emulated and hardware experiments and to expand the scale of the physical infrastructure by adding some virtual infrastructure and wiring it together. Could have tutorials as another potentially useful use case for emulators. Is you can have a tutorial without needing the actual hardware, although it's nice to have the hardware too, but you can learn on the emulator and then do on the hardware if you want. And also I really like this idea of archived experiments that can be run and reproduced either in emulation or on hardware. And I guess I mentioned cloud emulation integration, and usually emulators like Mininet and Mininet-Optical don't have a strict notion of virtual time. That's something that simulators tend to have. They tend to basically operate in real time because you're talking to the real software. You're talking to the SDN controller in real time, which is just running. However, you can also introduce this notion of sort of scaled time if you want to imagine that the simulation is running faster than it actually is. So this is the idea of time dilation, where 1 second of simulator time might be like, you know, 1/10 of a second of virtual time. You can also implement virtual data rates. The Mininet simulator will give you maybe, you know, megabits or gigabits of data per second. But if you want terabits, well, you're not going to get that on your laptop or even on a big iron server. But we could just implement a multiplier that would give you a virtual data rate. So you could have your experiment appear to have a high data rate, even though its physical data rate would be much lower. And also parallel and distributed execution. Our initial prototype is serial, sort of linear, just so we could try to get it right. So to wrap up, what kind of we're proposing, and what I'm proposing today, and I'd like your feedback on, is this this idea of an emulated Cosmos optical xhaul network. I think we can implement this by extending our existing work on Mininet-Optical with special sort of features that are Cosmos specific to emulate the actual configuration of Cosmos, to support compatible devices so that controllers can move seamlessly between the virtual and physical infrastructure, and adding additional features to sort of make it more user-friendly and make it so that you could really learn how to use the system on the emulator and then work on the real hardware. And with that, I will take any questions. Can you guys hear me still?
Yeah, sure. You're there. So there was one question in the
oh yeah, let me look in the chat.
Yes, please look at a question and answer. So there was a question on the availability of optical Mininet.
Oh yeah, is it available for the research community? No, but we're still working on it. But we hope to make it available, you know, sometime in the near future, COVID and pandemic permitting. But yeah, the intent is that it's going to be open source, just like regular Mininet and the various extensions to Mininet, such as Mininet, Mininet Wi-Fi, which is done at, I think, CPQD, and MaxiNet, which is another parallel implementation of Mininet, and various other extensions of Mininet. But essentially, since they're built on the same architecture, it's certainly not trivial, but certainly possible to integrate all these things together. And if we look at if we look at the current Mininet-Optical, it has integrated packet optical. But yeah, the intent is, it's not fully baked yet, but we want to make it available. And if you're interested in working with it, let us know, because we may want some users over the next few months.
And then the second thing is, yeah, sorry, go ahead.
Oh, is there something? Oh, yeah. So I guess those are the same, most of the same
yeah,
questions.
Exactly.
Yeah,
So,
is there documentation? No, that's why that's why it's not available. I mean, any system like this, it's a large undertaking. We've actually been working on it kind of for a year and a half. A little bit of setback, but there's still a lot of work to be done, and we're looking for help. And of course, the other thing is that the Cosmos enhancements, that's really quite a bit of work. Very valuable work and highly leveraged. For example, if we implement some things like the Lumentum ROADM API, then that would also enable things like ODTN, which is ONOS's optical networking control. And I mean, there's a lot of synergy between a lot of these different projects. And I think the interesting thing is that like improving the simulator could be highly leveraged, not just for Cosmos, but for a bunch of other projects as well.
and that was actually my question. So how can we help this whole process, right? And what the Cosmos has to do to make it happen, right?
Yeah. So the standard ways of doing it, capital and labor, right? But also access.
Sure.
As capital, labor, and
Yeah,
access are the three things. So access to Cosmos, people to work on it, and money to fund people, like me and other people on our team to get it done. And so
yeah.
the other questions: is it possible to integrate it into another integrated emulator simulator, such as the traffic simulator that's built on Cosmos? The answer is, I don't know. That's interesting. So I'm actually a Cosmos noob, as you can probably guess, because I seem sort of clueless today. So feel free to correct me and educate me on Cosmos. I'm going to do the tutorial tomorrow and try to find out more about it. So potentially, yes. So the nice thing about emulators is they're real. You can send real traffic into them. So if you have something that can connect to the real world in terms of something like an Ethernet port, then you can basically plug it into Mininet-Optical. And obviously, you may need to do some trickery because you can't plug analog signals into a software emulator, right, without transducing them in some way. So you need to terminate the optical signal and then probably turn it into Ethernet packets. But if you can do that, yeah, and you can tunnel across the internet, and yeah, it's all doable. Oh,
And then that's the question.
not the network traffic simulator, the traffic on the road simulator. And yeah, no, that's a great idea, right? Which is basically simulate mobile devices like radios on cars and their locations, and then have that feed into to the simulation parameters. So yes, absolutely. I think it's a great idea. And I have this suggestion of what I call sort of an abstract endpoint simulator, where you don't necessarily simulate every last detail of the devices, but you simulate the things that are important to you. So a couple things that are important for mobile network simulation are which mobile access points can you see, and so you can direct all your traffic to that. Another is what the sort of error rate is, and the other, or what the data rate / error rate you get to each of those, and also what the delay is. So those are all things that can be modeled in Mininet. So if people want to do that, I'm happy to chat with them and help advise on how to make that happen. But yeah, vehicle traffic versus internet traffic, that's the cool thing about a city network. You have literal traffic.
There was another question. Will every
Yeah,
component in the DNTI?
Yeah, so you can, there's a Mininet mailing list that you can sign up on it, and you can send to the Mininet community. You can also email me. So
Okay, thank you very much,
This is
Bob.
Dan. Wait,
Oh,
so
Dan.
Yvonne, if I could jump in. So the answer to Jesse's question. So we benchmarked against GNPy, and so we've basically
GNPy,
got
yeah.
most of GNPy implemented. But you can do much more than just what GNPy does. And one other point I want to make. So we're actually doing pretty much every night we're collecting data off of Cosmos, and we're compiling a large data set for the purposes of training machine learning algorithms, and we're also using that data then to feed into Mininet-Optical, so we'll be able to use it to build our Cosmos models in Mininet-Optical.
Yeah, thanks, Dan. Yeah, that's exactly right. I will note that instead of using GNPy out of the box, we have our own simulator, our own implementation of it, which actually has additional features and which we can also be customized. So we can split out the if we want to, we could split out individual components. But yeah, we obviously have ROADMs. I didn't have them on my diagram just because it's simplified, but there are a lot of devices, right? So in particular, each link consists of multiple fiber spans and a boost amplifier after the ROADM to compensate for loss in the ROADM, plus compensation amplifiers along the links. And the amplifiers are can be SDN enabled as well.